Terpenes are natural products produced by plants that are formally oligomers of isoprene. So isoprene has the molecular formula C5H8, and as you can see, it has 2 double bonds in it, and it has branching at the carbon second from the end. So only 4 of the 5 carbons are ever in a straight line. So when I say it's formally an oligomer of isoprene, what I mean by that is it is not biosynthesized by taking isoprenes and putting them together. But these molecules do contain multiples of 5 carbons in terms of their number of carbons, and each 5 carbon unit contains a double bond and the appropriate branching. Okay, so let's look at some examples. One would be limonene, which is a 10 carbon unit. So I have a couple of blue lines going through it, showing you how this molecule can be disconnected to give the 2 5 carbon isoprene units. And then you can see each of those isoprene units, the one on the top and then the one on the bottom, has the branching at the 4th carbon that you would expect. Okay, we can have an alcohol present in our terpene. So this is an example of geraniol, which has an OH at the end of the chain. And then finally, terpenes can be a little bit bigger also. So farnesene is a 15 carbon terpene, so it's made of 3 isoprene units put together. And as you can see in this case, the 3 units are basically put together head to tail. If you think of the tail as being the fish tail that you get out of having those 2 methyl groups coming off the end there. So there is some nomenclature that we need to be able to use involving terpenes. So it turns out that there are no naturally occurring 5 carbon terpenes. So the smallest naturally occurring terpenes involve taking 2 isoprene units and putting them together to give a 10 carbon molecule. So these 10 carbon molecules are also called monoterpenes. 20 carbon molecule will be a diterpene, a 30 carbon will be a triterpene, and a 40 carbon will be a tetraterpene. As you can see from farnesene up here, there are also important terpenes with 15 carbons. So the name we give to that is a sesquiterpene. And just to remember that, just remember that the 150th anniversary of anything is the sesquicentennial. So here are a few more examples of terpenes, in which case I have the isoprene units circled in different colors. So myrcene, alpha-pinene, and beta-selenine, these are all completely carbon and hydrogen terpenes. So you have an example of 2 monoterpenes and a sesquiterpene. And once again, note the branching that occurs in each of the isoprene units. You can also have functional groups present in your terpenes. We already saw the example of geraniol, but you can have menthol, isolated from peppermint oil, and then camphor and carvone both have ketones in them. But again, they have that same, when you see these fishtails, you need to be thinking terpenes here. Even though camphor is a rather complex structure that has a bridged bicyclic ring system. A couple of other larger terpenes that you might be familiar with, these are both examples of tetraterpenes, are lycopene and beta-carotene. You met both of these structures in the lesson on color as being compounds that are highly colored. Lycopene, of course, is the red pigment present in tomatoes, and beta-carotene is the orange pigment, actually present in a lot of plant matter, but is most prevalent in carrots. And both of these, as I've said, have 40 carbons, but the reasons why they are so colored is due to the extensive conjugation of their double bonds that are present in these structures. However, if you look at them carefully, the reason they have all of these methyl groups sticking out at regular intervals is because they are in fact terpenes. So if nature does not make terpenes by polymerizing isoprene, how does nature make terpenes? Well, the answer is that it uses 2 building blocks. dimethyl allyl pyrophosphate and isopentenyl pyrophosphate. So pyrophosphate is nature's leaving group. You've already met pyrophosphate in the context of some reactions of ATP. So it has two phosphoruses linked with an anhydride oxygen. And if you think about cleaving the carbon-oxygen bond, putting the electrons onto the oxygen, you end up with the pyrophosphate anion, which is a very weak base. Therefore, pyrophosphate is a good leaving group. So cleaving this bond in this manner will leave a positive charge on the carbon. So this takes us back into the chemistry of carbocations. And in this case, if you start with dimethyl allyl pyrophosphate in particular, you end up with a resonance stabilized carbocation. So if you look at that initially, if you just look at the dimethyl allyl pyrophosphate structure and say, if this loses pyrophosphate, it's going to make a primary carbocation. Well, yes, that is true for one of the resonance forms, but if you remember, this is an allylic carbocation, and you had in the first semester to manipulate allylic carbocations to show all of the resonance structures. And this particular allylic carbocation has a second resonance structure that is tertiary. Okay, so therefore it is a pretty good resonance stabilized carbocation. All right, and then I want to end this lesson just by giving you an overview of the coupling mechanism that is used by nature to couple two of these isoprene fragments together. Okay, so we're going to start with the dimethyl allyl pyrophosphate and make the resonance stabilized carbocation. Now, carbocations, of course, want to get attacked by nucleophiles, and they can be attacked on one that has two resonance structures that are not the same like this, can be attacked on either of the carbons that bear positive charges in one of the resonance structures. But the terminal one is more sterically accessible to be attacked by a large nucleophile. Okay, so in this case, we've already dealt with the dimethyl allyl pyrophosphate. Now we use the pi electrons of isopentenyl pyrophosphate to act as a nucleophile, form a new carbon-carbon bond, and attack the carbocation. This will leave us with a new carbocation. This one is not resonance stabilized, but as you can see, it is a tertiary carbocation. And then all of these coupling reactions are, of course, enzyme catalyzed. So they're happening at whatever the pH is of the organism that is making them. So they don't happen under strongly acidic or strongly basic conditions, but rather specific amino acid residues within the enzyme can act as acids or bases. So a basic amino acid residue will then remove a proton. So we need to end up with something neutral, and we need to end up with two double bonds because it's going to be a monoterpene here with two isoprene units. So we're going to remove the proton, use the electrons in that CH bond to form a carbon-carbon double bond. You've seen some examples of this in the context of other reactions, such as, enol formation, enolate formation. And then using those electrons to form the carbon-carbon double bond gets rid of the positive charge and leaves us with geranyl pyrophosphate. Okay, and then all of the other monoterpenes are actually synthesized from geranyl pyrophosphate by further modifications. And then furthermore, we take geranyl pyrophosphates and we can put two of them together head to head, and that can give us a diterpene, for example. Okay, so I don't expect you to really know the nitty-gritty of the mechanism of this coupling reaction because it deals with some reactions that are outside the scope of this course, but you should still be able to overall follow the steps of it. Okay, so that's terpenes for you, and our next stop in our tour through the lipids is going to be phospholipids and related compounds.